All right, everybody. So today we're going to do another example. We're continuing on 4.5, which is optimization problems. Again, my favorite problems. Last video, I forgot to introduce my audience member, Michael Scott. Oh, sorry, not Michael Scott, Prison Mike. So he'll be joining us today. And on that last video, keeps me happy. So we're just going to keep him there because I love Prison Mike. Okay, so what we're going to do today is we're just going to go over a lot of examples of optimization. Like I said before, doing optimization problems just requires a lot of practice. So I highly recommend you're really focused on your homework when you're doing them and just try to get the most out of them because each problem is a little bit different, but it's good practice. And they're fun, and then they'll come up again in your Calc 3 classes. So that's good. Okay, so for this example, we want to find the point on the graph, f of x is equal to the square root of x minus 3 that is closest to the point 4, 0. So remember I said in the last video that it's a really good idea to understand the problem you're looking at so that you're able to come up with the function that you're trying to optimize and whatever range of numbers it needs to satisfy. In this case, the range of numbers it needs to satisfy is the function f of x is equal to the square root of x minus 3. But the question is that what we're trying to optimize? Are we trying to optimize this? Right? No, we're not. We want to find the point on the graph. So we want to find a point here that is closest to this point. So what does that mean exactly? So if we were to graph this function, I hope we all remember what our square root graph looks like. So remember that your parent graph or your OG graph of square root of x just looks like this. Or, okay, that was a bad representation of it. Well, it looks something like this, right? And so the square root of x minus 3 means that we shifted over to the right 3. So that means that at this point, 1, 2, 3, we have the graph. Let me get a different color. We have the graph here. So our function, our square root function looks something like this. Not super accurate, but it's just so that you can get an idea of the context of the problem. So this is the problem we're dealing with. And then the point 4, 0 is right here, 4, 0. And so what they want to know is what point in this graph here gets us closer to 4, 0. Is it this point? Obviously, it's not something that's way over here. That wouldn't really make sense. Let me take that out. So we know that it's going to be something around here, but how close do we want it? Is that going to be the line point? Is this going to be the point, or is this going to be the point? So we're looking for the point on the graph that gets us closer to the point 4, 0 from that point. That's what we're looking for. So we're looking to minimize the distance between this function here and this point here. Okay? And so that's why I said each problem is a little bit different. So just keep that in mind. So now we're going to be, we need to come up with our two functions. So for this problem, we are going to have a constraint and we are going to have an optimizable function. So we need to label what we're going to constrain and what we're going to optimize. So in this case, we are actually constrained to the function y equals, or f of x equals, the square root of x minus 3. That's actually our constraint here because we're looking for the point from there to the point 4, 0 that'll satisfy that. So we are constrained to f of x equals the square root of x minus 3. Now, we need to optimize the distance between this point from a point on the graph somewhere here. I know it's going to live somewhere right here to this point here. That's what we're looking to optimize. So we're minimizing the distance. hey, Michael Scott. Oh, sorry, Prison Mike. You remember something that has to do with the distance? Yo, the distance formula. I'm losing my mind. Okay, but yes, the distance formula. So if you recall, in order, when we're looking for distance, we could use what's called the distance formula. So if you recall, the distance formula is, so let me just put it on the side here in a different color, you know. So the distance formula is equal to d equals the square root of x minus x1 squared plus y minus y1 squared. So that's our distance formula. I'll erase that in a second because it's bothering me how much room I have. But that's our distance formula. And right now we're looking for the distance between this point, from a point here to this point here. So our point that we're trying to find the distance of is this point here. So we're actually trying to minimize the distance. Oh no. So the distance formula we're trying to minimize is the square root of x minus 4 all squared, because that's our point over here, plus y squared. So we're trying to minimize that. Okay, so let me just erase that distance for the minute. I just wanted you to see where that came from. So sometimes you have to kind of go back into your memory and go, oh yeah, what does it have to do with the distance? So it's a good idea to just practice as many problems as this as you can. Okay, so now I need to optimize this. So that means I have to take the derivative of this, set it equal to 0, and find the minimum value, right? Okay, good. We're on the same page. Problem. I have a function of two different variables, two independent variables, and I need to get rid of one of them because I don't want to differentiate this because that's not going to help me at all. But what I do know is that this really is the same thing as y equals the square root of x minus 3. So we can rewrite this function d to equal the square root of x minus 4 all squared plus, and then I'll put this like this, the square root of x minus 3 all squared. Perfect, beautiful, I love it. Okay, and now we have a problem here with just one variable, which is beautiful because now when I differentiate this, I mean, it might still be a little bit of a pain to differentiate because I have some inner functions and I have an outer square root function. So I know I'm gonna have to do chain rule, but it's still easier than having to do implicit differentiation, which wouldn't really take us anywhere for this problem anyways. So let's go ahead and just simplify. So good idea to pause the video right now and to try to simplify this function here. Okay. So I'm going to simplify it, but you pause that video and try it yourself. So hopefully you FOILed this part out, and then the square roots here are going to cancel each other out, so you're just left with x minus 3. And now I'm just going to simplify the inside together. I have a negative 8x here and a positive 8x here. I mean a positive x there, so that's going to make us 7x. And then 16 minus, sorry, you can't see me pointing. 16 minus that 3 is going to give me 13, so plus 13. Beautiful. And now before I decide to differentiate it, because I know in my head that I'm going to have to differentiate this, I'm just going to rewrite this so that when I do the chain rule, it's just a tad bit easier for my brain. Let me fix that. Beautiful. And so now what I need to do is I need to take the derivative of d to my distance formula, because remember, we're trying to minimize that distance. So that's what we're going to do. So now to differentiate this, I take the derivative of my outside part. My outside part is I pull that 1/2 over to the front, and then I get x squared minus 7x plus 13, all to the 1/2 power. Beautiful. Now, I still have to take the derivative of the inside. Don't forget that. Don't ever forget that, because that'll hurt my heart if you forget to take the derivative of the inside. I think I stressed that enough in class, right? Minus 7. Okay, so that's our derivative, but let's make this look a little bit nicer because that looks just ugly, because I know that we're gonna have to set this equal to 0. Remember, always have it set it equal to 0 because we're trying to optimize the problem. So, okay, so let me see. Oh, and this should be a negative up here. Okay, perfect. So since this is negative here, I know it's going to be in the denominator, so I'm going to rewrite this so that it's in the denominator. I'm going to get the square root of x squared minus 7x plus 13. And then my 2x minus 7 here, nothing was wrong with it. It's all positive. I mean, there's no negative powers. So I'm just going to go ahead and bring that up to the top. And my 2 is on my denominator, so I'll bring that to the denominator. And we need to set this, why is this just going up? Okay, we need to set that equal to 0. Okay, perfect. So we're going to set this equal to 0, and recall that if you have a rational function that's getting set equal to 0, you only really need to worry about the top equaling 0, like always, because if you have the top equaling 0, then your whole fraction will be 0. So then that means that 2x minus 7 is equal to 0. And so that tells me that my x value is going to be 7 over 2. And so this is my critical value, but it is going to be a minimum. And go ahead and, you know what, just for practice, go ahead and just for practice, just check that it's a minimum, because one, it's a good practice for these problems, and it's good practice if I ask you for the mins and max of any problem. So, just keep practicing, it's good. So I have my 7/2 here, and so I need to check it on the derivative over here. So I'm gonna, I'm sorry, our derivative was d. So we're gonna check it on d prime and d prime. And if you check it on d prime, right, check something like 1/2, and then maybe, let's see, 5 would be good. When you plug that in here, you plug in 1/2 into this, right, you're going to get a negative value. You'll get 1 here, minus 7. That's going to cause that whole thing to be negative. You're not going to get any negative values down here, because remember, this has to be greater than 0. So this is going to be negative. Looks good so far. And then if I plug in 5, well, then I'm going to get 2 times 5 minus 7. That's definitely going to be positive. So this is definitely a minimum value, which is what we wanted. And hopefully that works out. And now to find the y value, right? Because they want to know, I'm not done here, even though it seems like I'm done. I'm not done here, because if I come up here, they want to know the closest point to 4.0 that's on this graph. That's on that graph. And I only have the x value, but that's okay, because I know that this value here is on my function. And so now I just have to report that y value, so I can report that ordered pair. And so all I have to do is plug that into my function. Remember that y equals the square root of x minus 3. So then if I know that x value, all I have to do is plug it in. 7 over 2 minus 3. And so then after simplifying this, you'll get the square root of 1 over 2, which is the same thing as root 2 over 2. And so my ordered pair, so I'll put minimum point here, is 7 over 2. If you want to rewrite that as a mixed number, go ahead. And then root 2 over 2, and we're done. So that's our answer. And so this point is going to be here. So that's a little bit more than 3 3.5, right? So 3.5 is like somewhere over here. And then it's up √2/2. So it's somewhere over here, which is what I expected it to be. I expected it to live somewhere around here between the 3.5 mark. Maybe going a little bit further than 4 was a little bit too much, but that's what I expected it to be. And we found that exact point. So fun. These problems are so awesome. Okay, so now let me go ahead and pause this video. All right, so now let's move on to the next example. This is a very typical optimization problem, and it's a really good and interesting one. I think it's pretty fun, but before we go ahead and get started, I have some really interesting news. My nephew was just born literally a couple hours ago, and you probably can't see this, and then my phone is super cracked and I can't go get it fixed anywhere, but isn't that the cutest little baby ever? Yeah, okay. He's so cute. His name is Xavier. And unfortunately, I can't go visit him, but you know, that just made my day today. So I can't go visit him, even though, well, you know why I can't go visit him. Because coronavirus. So sad. The reason why I'm here, not in my classroom where I should be. But it's fine. We're making the best out of it. So let's go ahead, and now that you've seen the cutest baby ever, I'm so biased, we can now do this problem. Okay, so example, an open box is to be made from a 12 by 15-inch sheet of cardboard by cutting the squares from each corner and folding up the sides. Find the length of the side of the square that will give the box the largest possible volume. So here they're trying to optimize the volume. So that's something that we need to keep that in mind. We need to optimize the volume. And so the best thing here is you want to try to understand the problem. And part of the understanding of this problem is I know I'm going to have to optimize the volume, but it's a good idea to maybe draw a picture. So let's just picture what's happening here. So I have a box. Okay, and so I have a 12 by 15-inch sheet cardboard box. So I know I have a 12-inch. Oh my God, what happened here? 12-inch by, let's do 15 inches in purple, by 15 inches. And they want to cut squares from each corner. Now we don't know the length of this square, so let's just call them X. So what they're really doing is they're cutting each of these squares here. And so their length, we're just gonna call them X. So we're gonna call them X by X, X by X, X by X. So they're cutting this all up to make that cardboard box. So then they're gonna fold up these sides and make that cardboard box. Okay, and so we need to optimize the volume of this cardboard box once we cut up the corners and then fold it up. And so in order to do that, one thing we need to keep in mind is say, okay, what is the equation of the volume of a box? And that would be length times width times height. So hopefully you remember that. And so what we want to do is, if we wanted to write an equation for our optimized function, we are going to do that by writing the equation of the volume. So we can do something like V equals, let me go back to black. V equals some length times some width times some height. But now my question is, what's the length, what's the width, and what's the height? So we kind of need to figure that out, right? Because I know that my length, don't write this down, but would my length be 12 and then 15 and then my height is just X? No, it's not. That would be way too easy. We have to consider what's going on in this problem and if there's any constraints, because there might be some constraints for this problem, but we got to get a little creative with this. So constraints can come from many different ways. So for example, they can come from just identifying your domain, or actually having a constraint formula for your problem. So let's kind of picture what's going on with this box. So if we were to draw a box, by the way, I'm the worst at drawing boxes. Hold on. I was taught away. So like you draw them uneven, and then you draw the lines, and then it's like down, down. There we go. I got this. What's up, guys? Okay, I drew a box. Little things in life, I tell you. Okay, so now maybe if you picture the box in 3 dimensions, you can easily see what this box is going to look like. Okay, so my question is, I know that the height is going to be x because I'm cutting the squares x by x. So yeah, the height's x. I get it. It's cool. But now what's my length? If I'm cutting my length here, and I'm cutting x and x squares, then my length here becomes 15 minus however much I cut of this square x. So my length here is going to be now 15 minus 2 times x, because I'm cutting each of those pieces of x off. I don't know how big of an x I'm cutting off, but that's how much I'm cutting off. And now for my length, the same thing. I'm now going to have 12 minus 2x, because for my length here, I had a length of 12, but now I have to cut off 2 x's. So now if I wanted to write an equation for my volume, I can, because this is my length times width times height, and now I have all of them. So it's going to be x times 15 minus 2x times 12 minus 2x. Perfect. And this is beautiful, because guess what? We only have one variable, and our function that we're trying to optimize is v. And when I have to solve for this, then it's all good. It's all good. I just have one variable. I don't have to substitute anything. It's perfect. So this is my equation of my volume, and it's all in terms of a variable x. Okay. But now you have to actually consider something. You have to consider something about the domain of your function. And you're like, it's a box. What do you mean? No, but we have to be realistic about what the size of x can be. Okay, now picture this. X cannot be 0, but it could come really close to 0. And the largest x can be, without eliminating the whole box, is 6, because we're cutting off 2 sides of this, right? So if I cut off 6 here and 6 here, then this whole side is non-existent. If I cut off 6 here and 6 here, I still have some room left here, but this side is non-existent. So I'm going to take my smallest side and say it can't be smaller than 2 times that, because that's what I'm going to be taking away. So it can't be smaller than 6. I mean, it can't be larger than 6, because then it wouldn't exist, and it actually can't be 6, because then it wouldn't be anything. Okay. So now that we have our domain, and this domain is going to come in handy later on in the problem. And so now what we want to do is now we get to optimize our function, which means that we're going to take the derivative of b prime. But before we take the derivative, actually, let's simplify this problem here so that we multiply everything out and get it a little bit easier. So go ahead and do that, and then I'll do that myself too. Okay, so that's what I got after I multiplied everything out. And so now if we want to take that derivative, go ahead and pause the video here again and take the derivative for yourself, and then check back with me in just 1 second. So hopefully you guys got that. And now we need to set this equation equal to 0. Beautiful. Now what I'm going to do is I'm going to factor out a 12 because they're all divisible by 12 and move it over to the other side and then move this x to be positive. So I'm going to factor out a 12. When I factor out a 12, I'm going to get 15 minus 9x plus x squared, which equals 0. And then I'm going to do x squared minus 9x plus 15 equals 0. And now we can try either factoring or we can do the quadratic formula on this. We'll get 9 plus or minus the square root of 81 minus 60. Oops, eraser. Minus 60 divided by 2. Okay. And so remember with the quadratic formula, you get two problems. You get two answers. You're going to get 9 plus the square root of 21 over 2. And then 9 minus the square root of 21 over 2. Okay, so we have these two answers. And so now we're wondering which one is the actual answer. Well, if we actually approximate them and put them into our calculator, here we're going to get about 6.79. And for this one, we'll get 2.21. Okay, so we have these two values for our x value. But remember that we said that the domain of our function x is between 0 and 6. Because if I accepted this answer, 6.79, there's not even enough to cut 6.79 on each side. That's like physically impossible for this box. So we actually are going to just go ahead and trash this one here because it doesn't make sense for the context of the problem. And so this is our answer here. So we will cut. So we need to cut x equals 9 minus square root of 21 over 2, which is approximately 2.21 inches of each side of the box. These are like one of my favorite problems. There's always a box problem in all these calculus books, and they're fun.